Okay, section 3.4 is writing, well, which is something I suffer at. Okay, writing direct proofs. Okay. Sometimes these are called paragraph proofs. Okay, or direct proofs. It just means, look, you're going to lay out your statements and reasons in sentences. Okay, and just write out a logical argument that says, hey, this happens, and this is the reason, and then this happens, and then this is the reason, and so on. Okay, so number 3, proof type number 3 is a direct proof. Okay, in a direct proof, the hypothesis of the theorem is assumed to be true, and the conclusion is proven is proven as a direct result of the assumption. Okay, so we're going to assume that it's true, and then we're going to just build a case that it's true for everything. Okay, so let's do some proofs here. Example 1. Prove the following theorem. Prove the following theorem. Oops. Let's not do that. Prove the following theorem. Theorem. What's a theorem? The square of every odd integer is also odd. The square of every odd integer is also odd. Okay. Okay, proof. Okay. Well, we've got to introduce an odd integer. So let n be an odd integer. Okay. Since n is odd, n is equal to 2k plus 1 for some integer k. Okay. Okay. Plug in 2k plus 1 into n squared to obtain n squared equals 2k plus 1 squared. So now let's square this guy, lining up my equal signs. This is 2k plus 1 times 2k plus 1. Let's FOIL this out. This is 4k squared. I don't need the parentheses anymore. if I FOIL it out, 4k squared, k plus 2k plus 2k plus 1. So this is equal to, come on, bro. This is equal to 4k squared plus 4k plus 1. Okay, now I'm going to be a little sneaky here. I'm going to factor out a 2, not a 4, factor out a 2 from the first two terms. So this is 2 times 2k squared plus 2k plus 1. Okay. And then what we can do is we can call this thing m, which, and we're going to say, look, m is an integer. Therefore, n squared ended up being 2m plus 1, which is itself an odd number. Okay, it's in the form 2 times something plus 1, where m is an integer. Okay, so so let m equal 2k squared plus 2k. Thus, n squared equals 2m plus 1, where m is an integer. If k was an integer, and we just square it, multiply times 2, and then add 2 times the integer, well, then it is itself an integer because it's closed. Integer multiplication and addition is closed. Okay. Okay, we could even say that due to the closure property of integer multiplication and addition. Okay. Comma, we'll say and, since k was defined as an integer. Boom. Okay. Thus, since n squared equals 2m plus 1 is in the form of an odd number where m is an element of the integers, n squared is also an odd number. Okay, therefore, what? What did we prove? We proved that the square of every odd integer is also odd. And then we have our little, look, we proved it. A little colored in square. Okay, sometimes, okay, so that we did our first proof. Look at that. Isn't that awesome? That's awesome. Okay. Sometimes it is really hard to know where to start in a proof. So we use what's called brainstorming. We use our brains. Okay. We use something called brainstorming and scratch work to help us with this process. Okay. So sometimes it is really difficult to know where to start on a proof. We use brainstorming and scratch work to help with this process. Right? So let's do another proof here. Example 2. Okay, prove the following theorem. A theorem that we're proving. If x and y are positive real numbers, then x over y plus y over x is greater than or equal to 2. Okay. That's the interesting one. Okay, so we definitely need to have some sort of x value. We definitely need to have some sort of y value, but how the heck am I going to prove that some fraction plus another fraction is greater than or equal to 2? Yeah, I don't know. So what we might want to do is we might want to do some scratch work where we just kind of play around with this equation, play around with this inequality. So let's do some scratch work. Okay, x over y plus y over x is greater than or equal to 2. Okay, what I'd like to do maybe is get a common denominator. Okay, I notice that this guy over here has a y, and so maybe I can multiply x over x, and then x over y, plus y over x times y over y. Okay, those are just one, so nothing affects the other side. This is x squared over xy plus y squared over xy is greater than or equal to 2. Okay, that's good. I like that. Then this becomes x squared plus y squared over xy is greater than or equal to 2. Okay, so I did some algebra there. Okay, I'd really like to make it not a fraction because fractions scare me. If x and y are both positive, then if I multiply both sides by a positive number, it shouldn't affect the inequality sign. As long as these guys are both positive, okay, as long as x, okay, x is greater than or equal to 0, it's actually greater than 0. It's positive, right? They got to be positive. So x is greater than 0 and y is greater than 0, then it kind of is unaffected. Okay, as long as those guys are same, given that x is greater than 0 and y is greater than 0, then, okay, because yeah, we can't divide by 0. That's why, and it has to be positive. We couldn't even have 0, x to be 0, y to be 0 to begin with, because we would end up dividing by 0, which is not good. Okay. Okay. So, but we can multiply through by xy. It doesn't affect the inequality. We get x squared plus y squared is greater than or equal to 2xy. Okay. Anything that I can do with that? Well, what if we toss 2xy to the other side? We got x squared minus 2xy plus y squared is greater than or equal to 0. Okay, so this tells me that this thing over here is positive. Okay, I can factor this guy into x minus y times x minus y, which is greater than or equal to 0. And I could rewrite that as x minus y squared is greater than or equal to 0. And that is a true statement. I know that's true because any number that's squared, whether it's positive or negative, is going to be greater than or equal to 0. Okay, that's one of those things that we could assume. That's one of those 5 assumptions that we could assume back in 3.3 was that the square of any real number is greater than or equal to 0. So square of any real number is greater than or equal to 0. That's a true statement. Okay. So the thing I want to prove is up here. I want to prove this. And so what I would want to do is I want to build a bridge to that statement using, another statement that's a true statement. Assume that this is a true statement, true. By definition, that's true. And so we would actually want to work backwards in our proof. In the proof. Okay, so our scratch work can give us the idea of how we want to work backwards in the proof. Okay, so let's go to the proof now. Let's prove this to be a true statement. Okay, first I've got to define some of these values x and y, and then I got to get to this statement here, and then it's just simple algebra to get to the thing that I want to prove. Okay, so proof. Let x and y be positive integers. Okay. No, we just want real numbers, right? Yeah, real numbers. It's fine. Positive real numbers. Doesn't have to work with integers. Positive real numbers. Okay, that is, or in other words, okay, in other terms, x is greater than 0 and y is greater than 0. Okay. Okay, then x minus y is also a real number. It could be positive, it could be negative. Okay, it could be positive, could be negative, we don't know, but it's all good. Okay. Okay, therefore, x minus y squared is greater than or equal to 0 because the square of any real number is greater than or equal to 0. Okay, greater than or equal to 0. Okay, so using x minus y squared is greater than or equal to 0, we can obtain x squared, we can obtain what? Come on. X minus y squared okay, greater than or equal to 0. Okay. Then we can say x minus y times x minus y is greater than or equal to 0. Then we just kind of follow our logic backwards. Okay, and we say, well, this is x squared minus 2xy plus y squared is greater than or equal to 0. Add 2xy to both sides. We get x squared plus y squared is greater than or equal to 2xy. Okay, divide both sides by xy. Okay, and so we get x squared plus y squared over xy is greater than or equal to 2, since x is positive and y is positive. So I'm going to separate this x squared over xy plus y squared over xy is greater than or equal to 2. And then we're going to cancel x over y plus y over x is greater than or equal to 2. Therefore, okay, if x and y are positive real numbers, then x over y plus y over x is greater than or equal to 2. End of proof. Okay? Okay, and that is 3.4.